Um, so, do you remember what we're up to? Is it making any sense?
Fours.
What is this crazy F equals MA anyway? So there's really the only physics we're doing is F equals MA. But it seems to only be complicated by you guys figuring out vectors, right? If everything was in one dimension, this would all be easy.
The homework felt a little confusing.
And of course, we're only doing it in 2 dimensions, so keeping it pretty easy. So, are we ready to continue?
To where? Wait, what are we gonna learn for the next 2 weeks?
Oh, Henry, she wants the whole introduction you were talking about.
Yeah, exactly. That's what I've been wondering. Buzz just doesn't
Are we
like
gonna
that.
get our finals back to look at?
Oh, yes, I have them right here. Can you remind me at the end of the class so we don't get distracted?
Oh, yeah.
Yeah. Okay, well, we're gonna finish this stuff with forces, which is mechanics. We're gonna, F equals MA, we're gonna add in friction. And then we're either gonna do a section on energy or go straight into special relativity. I haven't decided yet. We'll see how long it takes us to get through this.
Special relativity.
Yeah, special relativity you're gonna have fun with, even though you'll have moments of pulling your hair out. Okay, so what do we have to do with this stuff? What didn't you get on the homework?
The last one.
Or can you
It
spend?
was a little confusing.
Can you spend a little time comparing and finishing it? Together?
Well, the last one was the one that didn't.
What was that about?
That
The
one
pulley
was
is
2
not-
objects with masses, and then they're like on a pulley system, and they're going like, woo, and they have like acceleration.
We did that one in class.
We did do that one in
I
class. I got it correct
forgot.
in class, but I got it incorrect on the homework.
Yeah.
Oh, the poly one. Yeah, we did do that in class.
We did it.
Because I got confused because I said, oh, okay, it's going like 30 newtons down, and but,
It's the exact same problem, different numbers.
Okay, that's
right?
exactly what I did, and my acceleration was ill.
These are different numbers, but same problem.
yeah,
That's
but
okay.
it was just,
That's exactly what I
It's
did.
just like,
Hold
it's
on.
one of those
50
questions
minus
where I would
C
understand
equals
looking at the
5A.
answer, but I
And C
wouldn't.
I got, is
equals
it 20
30
newtons?
equals
It's
by
20
myself.
newtons up and down, right?
Lyle,
Yes.
talk me through it here,
Okay, if I
and talk
start-
me through what you did and didn't do here. So,
Why do
do we
my
have the masses?
acceleration is equal to 10?
Yes, so the mass of the one on the left, the smaller one, is 3 kilograms. And the mass of the one on the right, the bigger one, is 5 kilograms.
okay, so you know what's gonna happen, don't you?
It's gonna.
Yeah.
Yeah, and you know that if this one accelerates this way, then that means this one's gonna accelerate that way with the same magnitude, just different
Yes.
direction, right?
Yeah.
Uh-huh.
Okay.
Well, maybe.
Okay, so what else? Is that thing in your way? Because I can move it.
Yeah, but it's okay.
But, you know, I had it there and you moved into the way.
That
of
is
it,
true.
basically.
But now I,
We're setting it up for, skiers. That's gonna be too close. I don't wanna get too far off to the side, cause then, but let's see what we can get. I hope they can sort of see that.
And now,
Can you
I
see,
can
Lily?
see right now, if you right over there, I
Yeah.
wouldn't, but I'll figure it
Maybe
out.
you'll have to move somehow.
I'll figure out.
Okay, alright. Alright, Wow, what do you do next?
so then, we can do individual, so whatever the diagram is
Free
called.
body
Free body
diagrams.
diagram.
And actually, another way of thinking about that is just looking at this block. You know this block is gonna drop.
Yes.
And why is it dropping? Because gravity's pulling it down, right? And you know that gravity's pulling it down with the force of gravity, which is gonna be mg, which in this case is gonna be 50 newtons, right? So you know gravity's pulling it down. Yeah, what? Keep going. But it's not just gonna fall like that because the rope's pulling it back up, right? So a free body diagram for this should just be like, you know, there's that thing, what forces reach across that imaginary barrier, and just pull on it, what external forces. And so now when we write F equals ma for that, what should I write? When I write that the sum of the forces equals the mass times acceleration, what do I get on those two sides of the equal sign?
20.
Well, So there's two forces.
So I did wrong.
There's this one minus that one.
Yeah.
So I could start in general and say the force of gravity minus the tension is the mass times the acceleration.
Well, you,
And,
never mind, yeah.
and so that's gonna be 50, oops, I don't know T.
Is the tension just how much the other one is pulling back on it?
Yeah, that's
Well, that's
what I
what the
thought.
rope
Well,
is pulling.
hold on now. What did you say?
The tension is what the other one's pulling back on it was.
The other one being this guy?
Yeah,
Yeah,
and that one is also mg, but that mg is only 30 newtons.
yeah, but we're not doing that. We're doing this guy. Cause I'm trying to get you to get intuition around the fact that any object, you know, its acceleration is gonna be predicted by the sum of the external forces acting on it. And you don't care about anything else that's happening anywhere in the universe, just what's happening to that guy. Cause that physics is always gonna work. So we know this mass is 5, and we know that acceleration, we don't know the acceleration, right? So F equals ma for the first mass gave us this. And then, can you tell me the same story for the other mass?
Yes. Is it tension pulling it up?
Let's see if Lyle can. I think she can.
Okay, so.
Oh
you
yeah,
have
I should
force
draw the
of
forces,
gravity.
right?
Hmm?
I should draw the forces.
You shouldn't do that.
So now I'm looking at this guy, right? And what forces act on that guy?
Gravity,
Okay, and do you know by how much?
30
Okay,
newtons,
and what else?
the tension of the rope.
The tension. And we don't know what the tension is, we just know that this tension is the same as that tension.
Yes. Yes. Oh, okay.
Okay, so now for that guy, we want to do, again, sum of the forces is mass times acceleration. So, on this side, if I want to write 3 kilograms times the acceleration, is it okay with you if I call that A the same as this A?
Yes,
Yeah.
Yeah, why?
because they're connected.
Yeah, they're connected. And if I call that acceleration going in that direction A, then I need to call this force positive.
Well, no, you'd have to call that force negative, because,
You say F
no,
plus
you'd have
T
to
and then
call it
FG
positive,
minus
never
T.
mind. It's going
Yeah,
in the direction.
because if, let's say we found out that this was accelerating down at 4 meters per second squared, that means this is going up
Right,
at 4 meters
yeah.
per second squared, so it must
Should
be
be
being pulled
negative
up.
A.
Tension is
So I
pulling
can
it up.
say 30 plus T.
Wait, so is T
So-
gonna be negative or is
No,
A?
I'd say T minus 30,
Oh, okay.
right?
Oh.
So T is pulling it up, 30 is pulling it down, and that
Oh,
will give an
yeah.
upward acceleration.
Yeah, okay.
So now I have 2 equations and 2 unknowns. So I just need math.
Cool.
And the easiest way to do that math is to just add those 2 equations together. And if I add the left sides, I get 15 minus 30, because the t's cancel. I add the right side, I get 8a. And so, whoops. I get a equals 20 over 8.
And then you can figure out.
Take a big old tension.
2.5.
Yeah, that's acceleration.
So what do you think of that number?
Makes sense.
Why does it make sense?
I guess it's accelerating at that speed according to the math. It's going.
It's accelerating. Why
and
does the
it's gonna
number
be
make
less than
sense?
gravity.
It's gotta be less than gravity, so it's gotta be less than 10. And then you look at that thing and in order to get down, it's gotta pull the other one up.
Yeah.
And it's a little bit lighter.
So it's pulling up with that speed.
I mean, if they were the same mass, we should expect to get 0. Lyle, what do you think about all that?
That is great. I
Kiefer,
like that.
were you doing something different?
I think you're doing the same thing.
I I understand why like on the left there's 50 minus t, on the right it's t minus 30, but I like don't. I understand why you did it, but like I don't think I would like put that together.
So, the story then that will always work for you is mechanics problems, draw the diagram, and then go in for each mass and draw a free body diagram, which means drawing the real external forces. And if you know how much they are, that's great. If you don't know how much they are, that's great too. Just label it, right? And then the next step is to apply that to this idea, right? This is all the physics, it's all gonna be right there. And so, we got an equal sign, we got, and so those are the external forces acting on that mass. And then that'll tell you something. It won't always tell you the whole answer to the problem. But this has to be true. So whatever A turns out to be, 5 times A has to be 50 minus T, right? Because this 50 minus T turns out to be the net force.
So
Like-
the 50 minus t is the 50 is Fg, and minus t is because tension's pulling it up. Over there, t minus 30. 30. But if it's being pulled down to 30, but tension's pulling it up, why isn't it 30 minus t over there?
Okay, so I could have, if I had, let's say I had a block on a table, right? And I had T and 30 like that, right? I could say T minus 30 equals MA, right?
Yeah.
And actually, let's even make it easier. Let's make this like 50 and this 5, okay? So I could say, 50 minus 30 equals 5A. And if I solve that, I get 20 equals 5A, I get A equals 4. Now, that's not only a number, it tells me the direction, because that's now a positive number. And so when I wrote 50 minus 30 instead of writing 30 minus 50, I was already declaring that I had an x-axis going this way. That's part of why in the beginning of the year, when we were doing projectile motion and all that, I always said, draw the axis in. You're modeling this fall off a thing, draw the axis to say what's going on. So I get positive 4, right? Now, what if I had decided instead that my x-axis went that way? Okay. Then I would probably write this. I write it as 30 minus 50 equals MA, and so I get minus 20 divided by 5 equals A, which is minus 4. Different answer. But this minus 4 is in this universe. So minus 4 meters per second squared means I'm accelerating that way, which is the same thing as what happened here, right?
If you go back to the pulley,
So-
can you draw an axis on that?
Right. So it's a little trickier on the pulley. So on the pulley, when you had T and 30, right? If I wrote it as 30 minus T equals MA, and what was the A, 3 or something? 3 equals 3A, okay? Then if somebody came along and told me what T was, I could solve this. You're gonna find out that T is greater than 30. And so that's gonna make this a negative number, which is gonna make the A for this thing negative. And since I just called 30 down as positive, that means it's gonna go up. And I have more to say about that, but you look like you're catching up.
Okay.
So this is an if, right? If I did it this way, and in fact, let's just go back for a second and find out what T is. Let's see, 5 times that's 12 and a half. T is, 50 minus 12 and a half, 37 and a half?
Yes.
Okay, so T turns out to be 37 and a half, so, in other words, 30 minus 37.5 equals 3A, so this would have been minus 7.5, so minus 7.5 over 3, sure enough, is minus 2.5. Okay, so I could have done it that way, but if I was doing it that way, what I should have done is I should have said, this is like A1 for the acceleration of this block. And then the other one was like A2 for the acceleration of the second block. But because I know that A's are the same, I didn't label A1 and A2. And so if I'm gonna call them the same thing, if this A is the same thing as that A, right, then when this comes out to be positive, that better come out to be positive. So, and if I look in the diagram, when I wrote 50 minus T, A positive would be down for this guy. And since he's connected, if he goes down, he goes up.
So A positive on the right is down, A positive on the left is up.
Yeah. Because they're coupled.
Okay.
There is another way to do it. The other way to do it would be to say, I don't care about the rest of the universe, I'm talking about this, and I'm gonna call this A1. So this was A1, right? And now I have an equation. And then you could have gone over here and said, I'm gonna make A2 down positive, right? And if you did that, you would have said, 30 minus T
So then there'd be
equals
negative acceleration. on the
3A2, right? But now A2 is not equal to A1, so now you have two equations and three unknowns, okay?
So,
And so you need a third equation, and the third equation would have been A2 equals negative A1 because of the way the rope works.
okay, can I just go back to T minus 30? So, T is the greater force acting on that.
Yes,
So,
but that's not why it's positive.
but because it's greater, you, just like intuitively, T is the greater force and you're subtracting 30 is smaller force, right? Because the bigger block is pulling more.
Intuitively, yes,
Okay.
but not formally. Formally, it's positive because we've decided up is positive.
Okay. I understand that you do that. I just need my mind to remember it for a reason, so, okay.
The reason we're doing it is so that we don't have to do this.
Mhm.
If you just said, I'm looking for the acceleration of this first block, and I'm gonna call it A1, and you got this equation. Then you said, I'm looking for the acceleration of this block, and I'm gonna call A2, I'm gonna call A2 down like that. Then you would have written that equation. And then you'd have this one and this one. Two equations, three unknowns.
Yeah.
Ah, but the rope says this, the way I drew it. So why not decide up front that A2 goes up, and then suddenly A2 equals A1?
Mhm.
Save yourself
Okay.
time. Yeah, we beat that horse to death, huh? So, after you do this, you can solve for T, we just did it, right? We found T is 37.5. Can you check to see if that makes sense? How would you check that?
Plug it in and see if the acceleration is the same for both.
Yeah, it should work on both now. You should be able to come in and say, let's see, 50 down, 37 and a half up. That means 12 and a half down. Divide by 5. Oh yeah, it's a half. Same thing over here, 37 and a half up. 30 down, that's 7 and a half up. Divide by 3, that's 2 and a half, right? It all makes beautiful sense. Now, okay, no, I'm not gonna right now. I'm gonna show you something else. What about all the other problems? Do we need to visit those before we do something new and exciting?
I wanted to.
Let's do something new.
Yeah.
Even though I could have another, it's just more like I need to take a second to process for 17. Like, it's
Which one's
just
17?
like 17 is basically there's like one rope that's angled 6. I don't know how to describe it.
So the thing
It's
is
like-
hanging like this, where there's a thing with two
Yeah.
ropes, and there's two different angles?
Yes,
Yeah.
one is the
Oh,
left
you
is
want
60 and the
What
right
one's
is
30, one's
30.
30 and 60?
Yes,
Cool.
And the tension that it distributes is 150
is 150
newtons.
units.
Or that's its weight.
Here?
Its weight is 150
I
newtons.
see. Okay, yeah, so this is one of these little, like, theoretical tricks, right, where you go in and you say, I'm gonna do a free body diagram for that knot,
Mhm.
right? That knot, I don't even know the mass of it, and I
Yeah.
don't even care, because I know that the sum of the forces has to equal 0,
Yeah.
so the mass times acceleration, it's gonna be 0 anyway, so, yeah, so it means you've got 150 newtons down, apparently, and you've got something over here, F1, and something over here, F2, or T1, T2, whatever you wanna call it.
Yeah.
And those three vectors have to add to 0.
Mhm. No, it just took me a while to like, because the way it's drawn, if it's like an actual rope and it's hanging there, it'll be easier for me, but because it was like drawn like that, so I would like, it took me a while to think that the rope on that side and this
Yeah.
one will add up
It seems like it'd be-
equals to 0,
Yeah.
you know, like, not add up, like,
In
say.
terms of vector addition.
Yeah, say like the tension one, the rope on the left would be cosine 30 minus a rope on the,
Right, so
Right.
it is good to start, actually, let me just draw this one. It is good to start visualizing this stuff as you've done the solution. So,
yeah,
so when you take F1 and you break it up into these two components,
mhm,
that one's gone now. So now we're pretending we got this real force, and then these are like imaginary forces, right? They're the components of the other one.
yeah,
But they have the same net effect as that one. And then the F2 over here, that has that component and that component, and now that one's gone.
yeah,
And so now it's easy to see everything in the X direction is just that one and that one. Everything in the Y direction, there's 3 of them. There's that one, that one, and that one.
yeah,
And so we want to get acceleration 0 that way, and we want to get acceleration 0 this way.
So that means that,
So, yeah, so that means like this,
sine of 30 F1.
so
is gonna
this
have-
blue one, right, is F1 cos 30,
Yeah, it's gonna have to be the same as.
and up there is F1
Cos
sine
60.
30,
yeah,
and you split up the yellow ones, let's see, 60's there, so, did I do that right? 30,
Yeah.
yeah, 30's there.
Yeah, yeah.
And then this one, 60's here, so 60's here.
Mhm.
Yeah, so this one is F2 cos 60,
Mhm.
and F2 sine 60 is that one. So,
yeah,
F2 sine.
so F2 sine 60 plus F1 sine 30, have to add to 0. Oh, no,
It has to
minus,
add to
Minus.
150.
150, yeah, that one.
right, 4 minus 150.
Or minus
that
150
was-
equals 0.
Right.
From a conceptual.
That's in the Y
That-
direction.
That, I don't like when it's written out so, like when you look at the answer sheet, it's written out like that, and I like cannot understand.
Oh, wow, this is a skill you must develop.
Really?
Yes, get over the insecurity about it and just read, right?
Okay.
Right? So you gotta start seeing, right? You started with F2 and you projected to a component.
F2 sine 60.
And then in the X direction, we just got
Cosine.
F1 cosine,
It's saying F1 times sine 30, right?
yep,
Okay.
and then minus
I have to just write it out. Like,
F2 cos 60,
Yep.
okay, equals 0. And then what did you do? Did you find the sines and the cosines?
Yeah, cosine.
Wait.
And then you got 2 equations and 2 unknowns?
yeah,
I just
you don't need to find that one.
did, like, well, I just knew that if it's not moving, then there's gotta be the same force in the other direction, so it's pulling 150 up. And then I had a couple of angles, and they shared that common side, and I semantic trick, so I think I did that without
Well, so
writing
what
it
you
out.
did is you ended up with this equation with the equal sign there, because you just add the 150 over.
Mhm. Is that wrong?
No, that's right, I mean, if this equals 0, then of course 150. But when you say, because I know they have to cancel, I can write it that way,
Mhm.
I'm saying, you know they have to cancel because the acceleration is 0.
Yeah, that's what I meant.
Yeah.
So we don't really need
backwards
to
in there,
find
but-
the y and the x.
The video will come out right, right?
Yeah, it come out right, it's just your video is flipped.
What'd you say, Ron?
We don't like need to find the y and the x, right? We just use sine to find the tension.
Well, what did you do after this? Did you plug in values for sine and
I just
cosine?
said sine of 30 equals 150 divided by t, and then
What?
I think I got it right on the answer sheet. I'm pretty sure. Did you guys get 300 and 173 and 2?
I got,
3 something?
I got
Oh,
75
I
and
got
130.
130 in the direction, 75.
Let me
Yeah,
check
I
the
got
answer
50
sheet.
now.
I mean, how would you solve it?
So you'd have to make F2,
Yeah, make
a function of
F2
F1.
Okay, so you're gonna take this equation and just say that F2 equals F1 cos 30 over cos 60, right?
Right, which is gonna simplify
Which
to,
cos 30 is root 3 over 2.
1.73 F1.
So this is gonna be,
1.73 F1,
That's
so it's
what
gonna
I
be
was
root 3 1.
yeah,
Or F1.
7.3 or 7.23?
I think it rounds to 7.3.
Okay, 7.3 F1. Okay, so now you can take that,
Yeah, 1.73.
you can take this and substitute it in up here, right?
Yeah, put F2 into that, and then you solve basic algebra.
So, yeah, and
Sine 60 is like 0.86.
sine 60 is also root 3 over 2, and sine 30 is 1/2, right? So we're getting, oh, look at that, root 3, that's root 3 times root 3 over 2.
Yeah,
So
which
it's
is
gonna be 3 halves.
3 halves.
So you'll end up with root 3 over 2 times root 3 F1
That's a one, yeah.
plus 1/2 F1 equals 150. So that's 3/2 plus 1/2 is 2. So F1 is 75.
That is correct.
Okay, so let's go back and, oh, well, that's interesting. We found the magnitude without even finding the components. We don't have to do Pythagorean theorem or anything.
Yeah,
Cool,
exactly.
well,
I mean, you found that.
because we already did that.
Yeah, we already did that.
Yeah,
We did trigonometry instead of.
right. And so what's F2 come out to be?
130.
Well, I mean,
Yeah,
F1
so
is that
root
much.
3 over 2
minus
times, or root 3 times
150
that,
minus that.
130?
Yep. Just about.
So does it make sense that, F2 is bigger than F1?
Yeah.
Yeah, since the angle
You know?
applied, it's more, it's.
Yeah, how do you think about that intuitively?
Well,
Cause the other
Oh,
one,
this is the answer.
because of the angle, I don't know, it just feels like,
I mean, when you're headed
That's what I
straight,
did, I
that's the
was wrong.
most.
yeah.
Right,
most,
yeah.
That's sine 30
force
equals
acting on
150
it.
over t.
So that's 150.
Right, so if it
right?
was hanging straight down on this string, it'd be 150.
Yeah, it'd be 150, so the
Now
more
you
you
pull it
go out,
over a little bit,
Yeah.
Yeah.
it goes down a little, because that
You have
was
the right
taking
answer,
up
so I
some
was
of
just
the
like,
slack.
maybe I was in the
the most-
wrong.
And
Yeah,
so there's
1
more
degree
slack
centigrade,
on
yeah.
the road.
The most slack.
So, but also notice again, I know this is getting old, but 130 and 75 does not add to 150.
That is correct.
Wait,
That
what,
is
what?
correct.
130 plus 75 does not add to 150, right?
Because there's all, is it?
Right, it's because it's
also
vector
the-
addition, it's not
Yeah.
scalar addition.
So if we write it, we can write 130 plus 75 equals 150.
So, no, actually, and we haven't covered it, but, when I put an arrow over this to indicate that it's a vector, it means it's a whole different mathematical quantity than just a number with a unit.
Right.
And this plus this does equal, the negative of the mg, let's call it force of gravity. right? And I don't know if you've seen how you do these things. Okay. All right, let's see, what are we gonna have fun with next? Oh,
Oh,
so I can't remember, I know it should be my job to remember these things, but I can't
friction,
remember.
friction and, equilibrium.
Yeah, we're gonna do friction, that's
Final
equilibrium.
exams.
Huh?
Final exams.
I just wanted to ask, I wanted to have you do some tricky pulley problems.
Okay.
But before you do the tricky pulley problems, I just wanna ask you a conceptual problem. And this'll help us when we get into friction too. So, here's a frictionless surface.
Okay.
I got a box on there that's frictionless between that and the surface, no air friction anywhere, whatever, like say the mass is 5 kilograms, right? And I've got a rope attached to it that I can pull on, right? So I'm pulling it along and it's going at 1 meter per second at a constant
Constant
speed.
velocity.
Constant velocity like that. Now don't shout out the answer. Don't shout out the answer when after I ask you the question. How much force do I have to apply to have that happen? What must F be? So convince somebody else of your answer and then we'll shout out.
Wait, wait, wait.
Wait. You said
Wait,
to
what's
make
that?
it
What's
happen?
So I told you the scenario, right? It's frictionless. It's a 5 kilogram block. I've got this rope that I'm pulling on pulling on, and as a result of that, it's moving at that velocity. So what's the force?
So what's the
Talk
force
amongst
you
yourselves.
applied on it?
Talk
What's the
amongst-
force you pulled on it?
Yes, that's the question.
You have to know the friction, just double it.
No friction.
Oh, I thought this
If you
meant
pull
friction.
on it,
Yes, force.
5 meters for 1 second, and then you never touch it ever again,
Just
What?
pull on for 5
you
meters.
would get a velocity of 1 meter per
What
second.
for?
At t equals 0, it's moving at 1 meter per second. I'm just looking at the scenario where it's moving at constant.
So when you don't touch it at all?
So talk to each other, okay?
Wait, Buzz,
Okay.
it's already moving at 1 meter per second?
Yeah,
Yeah.
and it continues to do so.
So
And
what,
You don't have to
what are you
inject
trying to
any
do?
force
You're trying to
on it
keep it at 1
because
meter?
it's frictionless surface.
Yeah, so what's the answer?
Zero.
0.
0, right. Woo, good, we got over that, huh?
So hard. That was so hard.
Okay, nice. So what if I have a mass, 5 kilogram mass, and I'm frictionless, and it starts out at V equals 0, and now I pull on it at a force, actually, you don't even care if it started out at V equals 0, but as a result of that force, it's accelerating at 1 meter per second squared. Okay, how hard am I pulling on it now?
5 minutes.
5 meters.
5 newtons, right? Okay, so here's just a fun question. Maybe I've asked you this, I can't remember. All the years blurring for me now in my twilight years here. So why is there resistance? Like why, there's no friction, right? Why do I have to pull at all? Like, why do I have to
You need
pull
give
with
it
5
force
newtons?
in order to make it move.
Why?
Because the object is
Object is,
sitting there.
object is at
It
rest.
doesn't just
It-
start
Because little
moving.
particles on the
Unless,
floor
unless it's a force
are like
applied on
this.
it, it doesn't change.
Why not?
Because
Why
unless,
would it? Why would it change?
Because
Yeah,
it's
if it was just sitting there.
accelerating instead
because it
of
wants to be
constant velocity.
sitting at.
It wants to?
Yeah.
It has
It
hopes
wants
and
to?
dreams.
It wants to.
It has hopes
Is it-
and dreams.
is it having-
Exactly.
Is it having a deep emotional?
It's having a deep,
commitment?
it's thinking, I do not want to move. do
That's
I?
right, it wants to stay there,
I
yeah.
want to stay.
Why
My
does it-
head's not gonna move.
Have
if
you
I'm-
thought about why it does, how it does that?
Wait,
Because
can you repeat
objects
the
how it
question?
moves?
like to see
Yeah,
at work.
so you figured out we need 5 newtons.
Yeah.
Why do we need 5 newtons?
Which means it's fixed long.
How does that object put up a fight, right? I'm trying to pull it through a vacuum, frictionless vacuum.
Because.
Right, this could be out in space, right? I could take away the table because we already took away the air, made it a vacuum. We could move it out in space somewhere and just, here it is, just hanging out. Billions of
Still
miles from any
technically
kind of
moving,
black hole or
probably.
anything, it's not doing anything, and then I come along and yank on it. Like I decide, I'm gonna shoot this thing off at the speed of light and send it right into Bryce and knock his head off, right? But I give it a yank and it doesn't go the speed of light, it only speeds up, you know, it's 5 kilogram thing and I'm yanking on it with 5 newtons and sorry for me, it only accelerates at 1 meter per second squared, right? And I'm thinking, I'm out in space, what's the resistance?
Because
Is this
every
thing
object
speeding
will
up? How
remain
come?
at rest or uniform motion
how
in a
come it-
straight line
how come it
unless
doesn't
without
just take
change
off
of
really
state by the
fast?
action of external force.
When you pull something.
Because Newton said so.
When you pull something and it's against something, or it's against the air, or it's against anything,
Yeah.
that creates like an opposite force. But if it's just by itself, it's not gonna go backwards, because it's not moving against anything. So when you're pulling it, like,
So then shouldn't it move really fast if I pull it at all?
no, because of the,
Because the reactive force against the
Cause why?
yeah,
Cause why?
because when you're pulling it, it's interacting with,
pulling
like
back
the
at
floor
you.
or the air.
No, it isn't, there's nothing there.
Oh, I thought we were still talking about.
Okay, here, frictionless, no air.
Oh, I thought we were talking about if there is friction.
No.
Oh, okay, wait, what's the?
Because it doesn't have any momentum in it. You need to give it the speed. You need to
There's
give
no
it that
energy.
force. There's no energy in it.
Why would the molecules move if you didn't try to force them to move? They have no reason to actually.
Molecules move.
That's an
because-
Well, yeah,
interesting way to
but,
put
right,
it.
they always
But,
have like a
okay,
constant movement.
okay,
but I
that's
think the
fine,
logic itself-
that's fine, that's fine, if I don't push on it, they don't change their speed.
Right.
No.
If I do push on it, they do change their speed, right?
Yes.
Okay. But they don't change their speed infinitely, or up to the speed of light, right? They don't, like, there's, when I write F equals ma, right, I'm really saying that the acceleration I'm gonna get is only this big, okay?
Right.
So, given how much force I apply, right, the more massive it is, the less it'll accelerate.
Yeah. I almost think.
So this is my question. It's like, how can that possibly be so?
I don't know.
How does a
intuitively makes
mass
sense.
hanging out all by itself in space put up a fight? I try to pull it and it'll only speed up so much. How does it put up a fight? What is it, like backpedaling in the vacuum or something?
No, it's backpedaling at you. It's you're being backpedaled by the thing.
How does it accomplish that trick?
Because there's a reactive force.
You're just describing what happens. You're restating the law of physics we've discovered to be true. Right? We've discovered this is true. You go out and you try to yank on it, it's not going to speed up at the speed of light. And in fact, if it's got twice as much mass, it's going to speed up half as
Because
fast.
to speed it up,
And
you
we-
need more force. You only give it so much force, so it's only going to accelerate that much.
Why, how does,
So
we
if you-
know this is true. You're just, again, restating the rule. How could this universe create this rule?
Can I throw a shot in the dark?
Yeah.
So if you have in the void, if you have like a block or a ball or whatever, and you push it, all of those like molecules or atoms, they have to like hit each other
Mhm.
to move forward. So they're like wasting some of like the energy and force you put into it, bouncing off each other.
Oh, okay, that is true to the extent that the ball that you push on, when it leaves, now will be a little warmer than it was before because those vibrations will pass through the ball and bounce off the other side and go back and forth and leave the internal motion of those molecules a little bit faster, which is a higher temperature, and so some of the energy will be trapped there, and then, so a little bit less of the energy will be trapped with the whole thing moving as a collective. But that's not why here, because I could do this to one elementary particle, I could do it to one neutron, right?
So why
And
do
the
you,
story would be
so
the same.
question
One
is
neutron that
why?
weighs 5 kilograms.
Wait, let's look at the question itself. So the question is, why do I have to exert why does exerting 5 newtons in a vacuum or in a weightless space cause a 5 kilogram object to move with an acceleration of 1 meter per second squared?
And not more.
Right, so
Why
my
doesn't
answer,
it
I think,
infinitely accelerate?
because that's
the
the
object?
definition of force. The definition of force is the.
Yeah,
is the
but
movement.
you're right, but we also have a phenomenological understanding of force.
Yeah,
You
that's
know what it's like to be pushed against.
Right.
Wait, but so the question is just why doesn't things accelerate forever in space?
Or
Since it's
infinitely when they
infinite.
get pushed.
When they, yeah.
Cause I'm asking you to think about like the nature of our real universe, right? The nature of our universe, we know this is true, and we've come to accept it, and it makes intuitive sense to us, because when we push on heavy things, it's harder to get than it is on lighter things. So yes, indeed, okay, this is how our universe is. And in fact, this is how we define what mass is.
Right.
We don't define mass by how many atoms are in the air or something. We define mass by this property. It's the property of resisting acceleration, right? Is my language okay that that thing is resisting acceleration? Or in his language, it doesn't want to accelerate, right?
Because a thing only accelerates when you have force
Right.
acting on it.
But what?
But
Right, but how can that be so? How can this thing, like, let's say that's a neutron, right? What's it doing to like, aren't you mystified by this? I mean, how does it achieve this trick of not speeding up when it gets pushed on? I mean, it does speed up some, right? But it can limit how much it gets accelerated when it gets pushed on. Right?
it's painful.
It should be, yeah. Does it make any sense? Does the question make sense?
The question
Yeah,
makes
yeah.
sense.
Yeah.
You won't come up with the answer. I just want you to know the question.
What do you mean we won't come up with
Yeah,
the
what do you
answer?
mean?
Well, it took the best physicists like 75 years to come up with an almost complete answer called the Higgs boson theory, but
Oh,
it's and
Tell
he
us about the Higgs boson.
recently won a Nobel Prize to it, but it's still, there's a tad bit of incompleteness there.
isn't like the Higgs
But-
boson what gives mass? Yeah.
What is it?
The Higgs boson field, or the Higgs field.
The Higgs field. Gold particle.
But doesn't it seem strange? Or does it not seem strange?
Well, it doesn't seem strange because intuitively our minds have an
Experience it.
understanding of what is. Sometimes we know what stuff is, but we can't
Yeah.
give a reason for its definition or its exact, why it happens or what, but we have an understanding of what it is. So,
So,
this is
so,
pretty
ma-
similar.
so,
Think about the
so
Higgs field.
even when I tell you mass is, what is mass? If I ask you what is mass, everybody's gonna think stuff, right? Like if I say, I was on a spaceship traveling to Alpha Centauri, and I was way out there in interstellar space, and it was all vacuum, and suddenly I found some mass, right? Everybody would picture a chunk of stone, right? And they think mass is matter, which is atoms or elementary particles, right, put together. But I'm saying, no, mass is a property of an object that makes it hard to accelerate it.
Mass is force divided by
The force you would need to apply to accelerate it divided by the acceleration you get after you accelerated it. Right, so the mass goes up because the acceleration went down, right? Like, you compared same push on two objects, the one that didn't accelerate as much was more
More mass.
massive. And so we're defining mass as that property. But, think about that property. Think about how could anything in the universe have that property? Did you get the question, Lau?
Higgs field.
Completely and concretely, I understand what you were saying, always, but.
It's because of the Higgs field.
Is
I
that
just
what
thought
you
about
wanna
that.
hear?
Give me a
No, I'm
minute,
just
please.
kidding. I'm trying.
You know, so what part of it of my question are you not getting?
I don't know. We've just been talking about a lot of stuff, and now we're talking about all the different answers and things. And then I looked up the
And that was a
theory,
mistake, wasn't it?
and it was a
Yeah,
mistake
just make
because
it
it
sense,
showed me
that's
a
it, too.
scary little like explosion looking thing. But it's cool to think
Couldn't you
about.
just think
So
about
I guess
the
the,
Higgs
I mean, I
field
sort of
as
thought things
like
did go on forever
air
if they were in
friction
space.
for
and you kicked it,
particles?
you know?
well, we are kind of forced to
Why does
because
it
of our limited
accelerate?
Yeah,
brains.
because that's how we
But,
think.
yeah, but
Isn't that like-
actually, there's some
I was like
circularity
thinking
there
about
because if the particles that are setting up that are causing the friction, they
But
wouldn't cause
that's-
friction if they could be infinitely accelerated when you pushed into them. Right, so it's circular when you think about it that way.
Yeah. Yeah, because they're the thing that causes friction, right?
Real friction,
Yeah.
but you were talking about the Higgs boson.
Yeah,
So-
it's-
So
it's-
Lyle, I want you to get this.
Yeah.
You want me to ask you a less complicated problem? Well,
It was-
it's not any
it
less
was
complicated.
surprising.
Well, it is a little less complicated, but not much. So,
I mean, I get the question.
You
but
do!
Are we supposed to understand the answer?
no!
Oh, okay.
You're supposed to say there shouldn't be an answer. How could there possibly be an answer to that question?
Well, there is
Okay,
an
why
answer,
doesn't it
obviously.
accelerate?
Apparently there is, but.
Is there?
And
Horrible
K,
complicated.
and
Well,
K.
otherwise, it would, nothing would.
You think all good questions, well-formed questions have answers?
Yes.
You do?
What about
What
those,
about,
like,
what
giant
about the question
statues
of
on
existence?
that
Why does the universe exist at all? Why
Because
isn't there just
God decided
non-existence?
to
Why is there
There
some-
has to be an
Well,
answer at
There's a
some
bunch of like
extent.
little like bricks on.
What do you mean to
floating
some
mountains.
extent?
God,
Bricks
it's
were
God.
saying
I'm gonna be like Newton and believe it's God. Trust me, it's God.
I mean, people have their own thoughts.
Aliens.
It's the same with this,
Aliens.
with the matter, if the matter is resisting,
Yeah, I
then
know.
there is an answer for why it's doing so.
Okay, you can believe that.
Santa Claus?
Oh, yeah.
How does
You
it
don't, you
get
don't think
everywhere
that
in
there's
one
a
night?
reason for why
Yeah,
the matter
Wait,
is
so
resisting?
Buzz,
there
why
is,
were
but-
you
Some
asking
experts,
what-
physicists think so.
There is,
Like,
but
actually,
there is
like,
also,
each one of these.
when you think about the universe too, you also have to brush up against the idea that our entire understanding of everything is based on a certain set of unprovable and ununderstandable fundamentals. So the fact that there is space and there is time and there is mass, those are things we have to accept and start with to do all our business,
Yeah, but
right?
we
But
don't
you-
know why there is space, why there
Right.
is time. why
And
there
people
is
even
mass.
struggle to prove, like, why are there only
Why
three
mass?
spatial
Why is mass?
dimensions?
So
I mean, there is
crazy.
two.
Because by definition, that's what it's meant.
Because we
Yeah.
So,
define
Lyle,
what
here's
three
another
dimensions.
cloud, try this one. Okay, I let go of the book, you know what's gonna happen, right?
Yeah.
Yeah,
Yeah.
I guess I
Oh,
do.
you did or you didn't? Well,
Yeah.
what were you thinking might happen?
It's gonna
I thought it was gonna
fly.
go flying out the window.
You think it
but-
might go away? You think there's
I
any?
thought like you were gonna drop it, but
Oh.
instead you were gonna.
Oh, I
You're
see.
gonna make
Okay,
us think you're.
so if I let go of this thing, you know, 1 billion times, how many times is it gonna fall?
A billion.
1 billion times, yeah.
Probably every time.
Yeah, probably every time.
Probably.
We have quite confidence in that. That's the religion called physics, right? Is that the universe is ordered and these laws are.
Quantum
immutable.
mechanics thinks
Uh,
that things.
Okay,
just-
so why does it fall?
Because of gravity.
Okay.
Okay, gravity,
So, and-
I still
And
struggle
by
with
gravity,
that.
what do you mean by gravity?
There's big thing, not a lot of other things. Big thing pulls the small things.
Because
But
big
why?
because mass.
Really, that's what you think of as
the
gravity?
space-time
Actually, that's what a lot of
continuum
people
and
think
it
of as
pulls it down.
gravity. So you're saying, who's the big thing here?
Earth,
Earth, and who's the little thing?
look,
And who's pulling on who?
Earth is pulling on that.
Yeah.
Earth is gravity.
What about the book? Is
The
book
book
pulling on
is also
Earth?
pulling back, yes, because everything has gravity. You
Okay,
have
okay.
gravity.
Which way, who's pulling more?
You have gravity, it's
No,
true.
I know,
That's
I
why
know.
the book goes towards the earth.
If you and I have a rope,
Mm-hmm.
and I pull with 30 newtons on the rope,
Mm-hmm.
how hard do you pull back on the rope?
30 minutes.
Because of equal and opposite forces, right?
Well, that's if I'm standing still. The book's not still.
Doesn't matter. Whatever force I apply to you, you are applying an equal and opposite force to me.
Well,
So,
it's
so the
free
force
fall.
of gravity on this book is the same as the force of gravity from the book onto Earth.
But it
Okay.
but it still falls down. into
We still see it fall down. Now, the Earth should be accelerating up toward it too, right? Because somebody's yanking on it. This book is yanking on it. but because the mass of the Earth is so large, its acceleration will
Well,
be
yeah, but
great.
there
Wait.
is no rope connecting the Earth and the book.
There's gravity.
Wait.
There's a magic rope.
That's what I'm saying. See,
Invisible
people
rope.
say this all the time, and I know it's true, but I'm not just gonna accept it. I
Right.
wanna
That's
actually be able
right.
to like process why that is.
Okay, so this is what I was trying to get Lyle's goat with. Okay, so yeah, there's no rope. But there is a force.
Is you
So
lifting the book
what do you,
up?
so don't you think that's pretty magical?
It is.
Yeah.
Wait, Buzz, I have a
That's
question.
why
Gravity
it's
How
small.
does the Earth reach out and pull
Yeah,
on
no,
this
I-
book?
Earth got in like
Yeah.
pretty.
So,
it got-
Technically, gravity is a type of force, which means there's energy
Everyone-
there, right?
hit the Earth a little bit.
Yeah.
Where does the energy
Have
come
you
from?
ever-
Is it from you lifting up the book?
They literally
I don't know how to answer where does it come from. I know where the energy is.
Where is the energy?
It's literally in the field.
Is it in the gravitational field, or, I mean, I heard people say that like,
That's
this thing
interesting.
falls down because you picked it up and then there's inertia in it, and then you let go of that inertia and it falls down.
Well, inertia's the wrong word there.
Yeah.
But you did add energy to
Yeah.
the Earth book system. So in other words, if I've got, here's the Earth, you know, and here's the book, right?
Okay, but how did you create energy to the book?
Well, hold
You
on.
don't create.
Hold on,
energy.
here's-
That's what I'm saying.
bad.
So why?
Yeah, we are gonna
why-
get into a
how
lot of
do you
this.
give it energy?
Here's the Earth and here's the book, and, you know, let's say it's balancing on an icicle, almost massless icicle, and then the icicle melts, right? Global warming and all that, right? And then,
Of course.
so now the book falls to the Earth and the Earth falls to the book and they meet and they smash into each other. Not exactly in the middle, because the Earth doesn't move very much.
I guess it's about,
The book does
you know,
most of the
2
moving,
million
right?
times
Yeah,
larger.
yeah,
Well,
yeah.
more than that.
Okay,
There's also
so
books falling on the other side of it as
So-
well.
the total energy, gravitational energy in this scenario is less than this scenario.
So there's a bit of gravitational energy that's gone,
That's gone.
Used for-
And where it went into when these things smack together, vibrations
It moved a
pass.
bit, I mean, Earth moved a bit, still.
But then when they smack together and stopped, that gravitational energy is gone, and now it's in the moving molecules in both things that are set up from the
But that still
vibrations.
doesn't exactly explain
No,
why
that's right.
the
So-
Earth like literally reaches
No,
out and
so-
grabs things.
yeah, which is the question that Lyle is so anxious to know the answer to.
Come on.
Yes, Keith.
So there were problems with our projectile ball because when the ball went up a little bit, it was pulled on the Earth, so our measurements couldn't have been right.
Yeah, but when the ball was up there, it was pulling on the Earth, and the Earth was rushing up to meet it at the bullseye. Yeah.
Well, gravity accounts for that.
When
Gravity
those
is the
objects
measurement
heat
of
up,
those
planet.
two
when the book
objects
hits the
collide.
floor,
Measurement.
the Earth, does the Earth kind of like go back to its original position?
No,
No, Earth moves a bit, doesn't it?
Wait,
So
but-
Earth is always kind of moving in little like directions.
but what would happen is like, let's say we start here, right? As I lift this book, it's like I'm standing, you know, between the book and the Earth, right? I push on the book, I'm pushing on the Earth too, right? My feet are pushing on the Earth. So I'm pushing them apart, the Earth's moving down, the book's moving up, and now I let go, they come back together to the same place.
But why does it always still? But then.
But
So,
yeah, let's
but
focus
then,
on the
so
question.
then you would have to assume that everything would come from the center. You know what I'm saying? So if the reason that it's falling is because you're moving it from its
No,
original
no,
position,
the
that's
rea-
kind of what when you said that, that's what it sounded like.
Yeah, well,
I know that's not the
way,
actual reason.
another way, you can throw out all this F equals ma stuff and still formulate what happens in mechanics
Of course.
by using the principle that, when things are free to move, they
They
go
won't move.
downhill in terms of energy.
Sure.
But let's think about this magic force for a second. Because like, you know, everything we push, like I push against something, you can see me pushing it, and you get the sense of the force being applied, and you get the sense of the force being applied when it's a rope. But this is like action at a distance, right? This is like magically the Earth is somehow reaching out and sucking this thing down. It should be creepy as all get out, right? It's crazy what we take for granted.
Wait, but I was just wondering if like a really big planet that's like that hit Earth, will it like will you actually from like a distance away will you actually see it like
Move together,
move
yeah,
together?
yep.
Yeah,
Nice
the
to
Earth,
see that.
the Earth would move more actually than the object that was bigger than the Earth.
I mean like
But-
if it's a
Well,
So do you
Yeah.
wanna think about that? Do you wanna think about that magic?
yes, I do,
Is
and
it
also
like
I wanna.
magnets?
How do you think about orbits?
Oh,
Because if
really?
everything's pulling downwards, then
But she has quite,
It's like the
she has,
equilibrium.
she has,
Well,
yeah, she has a better
It's like
question.
the
What-
balls moving
better
and crashing
question.
into us.
right.
So, yeah, Lyle, what were you saying?
Is it kind of like magnets almost?
Yeah, you played with magnets, right?
Of course.
And you,
But magnets is both, well,
but,
yeah.
yeah,
But that's
magnets can
gravity,
attract and they can repel, right?
Exactly.
And when they repel, you feel them bouncing off each other even though they're not touching.
Mhm.
And that is action at a distance, right? And it is magic, the same way as gravity is
I don't know
magic.
about calling it. I understand
Right.
magnetism and.
You understand
polarity more.
magnetism? No, you
Well,
don't.
no, I don't, but.
But what do you
It
mean you
makes more
understand?
sense than
Why?
gravity.
How?
Because
Oh my God.
because magnetism is how electrons are interacting with things that aren't electrons or electrons themselves.
Yeah.
So that's like
Okay,
actual objects pushing
okay,
away
okay,
from each other
okay,
or not.
But
pushing
wait. So the electrons
Mhm.
are pushing against each other.
Right.
How is that less less magical than the two chunks of matter pulling on each other?
Because the electrons are an actual object.
This is an object.
Well, I know, but there's a bunch of stuff in between.
There's a lot of
It's
electrons.
still gonna fall if I take all the stuff away.
Gravity is like.
I know. No, I'm
Like
not
magnetism.
saying that, but I don't know. It seems more mystical
Is it-
almost
is
than
gravity-
when
Gravity does.
a
Let's be
little.
honest, we
The
don't know any of
magnets-
the fundamental
Because magnets,
words.
I feel like there's like magnetic field that I know there's
I think it's
gravitation.
just because you can hold the magnet in your hand.
Maybe I don't know.
I bet.
How can we explain, like, all the, can we even explain any of the fundamental forces?
Yeah, so it turns out this gravity force has been completely explained. That's called general relativity.
Oh,
Oh,
But you wouldn't like the answer.
what?
But you'd look it up on Wikipedia and think you sort of get it, but it's all misleading, ridiculous crap.
wait, I always
Yeah,
thought,
and it has to do with the structure of space and time.
yeah, like.
Wait, but we
Visually.
can't we
Like,
can't define.
I have a question, like, when you
I know.
visually see space-time, it's like, it's 2D. How do you use a 2D structure to explain a 3D world?
Right.
I don't understand.
And you, actually, what you need to do is you have to describe a 4D world, because you have to include time, that's another dimension.
Yeah, but
Right.
that's,
And it's hard to point in the direction of time,
How
so
do
it's
you
hard to
point
draw the
time
picture.
point that way?
But, yeah, so it does turn out that you can explain gravity as the curvature of space-time.
Okay,
which
but can
shouldn't
you even
mean
prove
anything.
that space and time operate the way they do? Because that seems relative.
Well, I mean, the fact that our predictions about gravity work is, and then the interaction between electrons is modeled better than any force that we know of, and it does have to do with the exchange of virtual particles, which is sort of like one electron creates out of nothing a particle and throws it at the other one,
Yeah.
and the other one catches it and throws it back, and then the first one destroys it. And so it has to violate conservation
Wait,
of energy.
destroys it? Then what would
Yeah.
you just do there? You just.
Well, it's like if you and I were standing on the ice and I had a bag of baseballs, I could throw a baseball at you and the kickback from it would make me go away. And then when you caught it, the kickback would make you go away. And then when you threw it, it would make you go away more. And when I caught it, it would make me go
So
away
wait,
more.
we're just
And then
gonna
I
keep
put it
on
back in my
going.
bag, it's like nothing happened. Except to do that, you have to create energy to exchange, to make the ball,
energy
exchange
go
the ball.
forward and being.
And so you have to violate the conservation of energy for a short period of time while you exchange this virtual particle, and then when you destroy it, you're back to net zero energy. And that can all happen within Heisenberg's uncertainty principle of momentum.
Heisenberg.
So, yeah, I guess we have to go, huh? So,
Heisenberg. What
so,
else
yeah,
do
we
you
need
do?
to think about weirdness a little bit.
Schrodinger. Cats.
So final exam stuff, maybe.
Oh, yeah, you wanna think about that?
Christmas
Well-
ornaments. Establish the size.
Ornaments, yes.
I wish it was.
Well,
Yeah,
I have
nice
a
and
question.
Yeah.
Pretty close.
That's-
Looks like
that's
those
pretty-
two big hills in your hometown.
Buzz.
Denver.
Yeah.
Question. People say that gravity only affects things that have mass, right?
Yes.
That's true. But
I mean,
light
how would
is
gravity
affected by
By-
gravity.
Yes.
But they say photons don't have any mass.
That's right. And so, so what happens is, it turns out that gravity is created by what's called rest mass.
Rest.
Yeah, and you can't get a photon to rest. If
No.
if the photon's always gonna travel at the speed of light, and, of course, there's another way of talking about that that makes what I just said wrong, but, so.
Why wouldn't you be able to get something that has mass to stop? Surely if you apply enough force, anything with mass will stop.
But photons don't have mass.
I thought you just said they did.
They have rest mass.
Can Buzz make a cute little drawing?
Oh, that only got one. I mean, if it has mass, then you should be able to feel it when like light hits you.
And you do.
That's heat in the sense of heat, no?
Right,
That
but it has
you?
such little rest mass that the
It's
push
Kiefer.
it gives you is so
That's not Kiefer.
infinitesimal, you can't measure it, but it is measurable, and in fact, this has been, yeah. The pressure, there is actual pressure, like mechanical force pressure from the light.
From light, yeah, that's how
Crocodile.
you put, there's
very
spaceships
tiny.
that uses that thing, doesn't it? There's mechanical force, but
Yeah.
it's so,
Oh,
it's just
on-
not, it's just so
Oh,
little
like-
that doesn't matter at all.
Right. Yeah, you-
What?
I haven't even looked at it yet.
Okay, yeah, you guys should.
My
What's
goodness.
wrong about it?
I
I
did
might want to
this
keep
for-
refreshing your thing, because I obviously I haven't. I don't think I posted
you have
homework
to
on
add
this last
FFG
night.
with the.
You know what's so funny?
That's so
actually?
that's like where I got
I
everything.
got the right answer, but when I wrote the equation, I wrote it with 10. But when I did the calculation in my
poor
head, I
Jack.